Okay, so we are recording this to the cloud. All right. All right, section 2.1, entitled "A Rectangular Coordinate System and Graphing Utilities." Okay. All right, the first thing we're going to do is hopefully review the XY plane. There is no way you could have escaped the XY plane if you've taken elementary and or intermediate algebra here at Mott, as the XY plane is a requirement in those courses. So this is hopefully review. We have a horizontal axis, which is normally, but not always, called the x-axis. The vertical axis normally is referred to as the y-axis. And these axes are at a right angle to each other. Usually tick marks are spaced 1 unit apart on both axes. All right, and notice when you go to the left on the horizontal axis, you're going in the negative x direction. To the right on the x-axis is to the positive x direction. Upwards on the y-axis is the positive y direction, and down on the y-axis is the negative y direction. The origin is the point of intersection between the x and y axes. These two axes basically partition our plane up into 4 quadrants: quadrant number 1, quadrant 2, quadrant 3, and the 4th quadrant right here. All right. The first thing that we normally do with the XY plane is we learn how to plot points. Okay. And here are some points that are plotted in the XY plane. To plot points, we always start at the origin and we move accordingly. So to plot the point 0,3, we would start at the origin and we would not move right or left because my x coordinate 0. We just move up 3 along the y-axis, 1, 2, 3. And so there would be the point 0,3 on the y-axis. To plot the point 2.5, 3.5, we start at the origin, move 2.5 to the right on the x-axis, and then we move up 3.5 parallel to the y-axis, 1, 2, 3.5. There would be the point there. This is the point -4, -3 in the 3rd quadrant here. We start at the origin, move 4 units to the left on the x-axis because the x-coordinate is -4, and then we move down 3 units parallel to the y-axis, -1, -2, -3, because that's the y-coordinate, and that would be the point -4, -3 in the 3rd quadrant. 2,0, I'll start at the origin, -2,0 rather, start at the origin, we move 2 to the left on the x-axis, and we stay on the x-axis because the y-coordinate is 0. Any questions how we're plotting points in the XY plane? All right, this should be something that's peer review, seriously, because bare minimum, even in elementary algebra, you learn how to start plotting points in the XY plane. And I know in intermediate algebra, you get a lot more serious in the XY plane than elementary algebra. Well, this is college algebra, ladies and gentlemen, so we're basically just introducing, or we're basically just familiarizing or bringing back the XY plane in our memory. And there's 2 things that I want to show you that we're going to be responsible for in the XY plane. And let's see here. The best way is to show you is this is figure 2-4 on in section 2.1, figure 2-4. You can write that down in your notes, section 2.1, figure 2-4. This is going to help us derive what is called the distance formula, which will enable us to compute the distance between any 2 points in the plane. Suppose I have 2 points plotted in the plane, point P here, whose x and y coordinates are x sub 1, y sub 1. And I have another point, point Q, whose ordered pair address is x sub 2, y sub 2. Since these subscripts on x and y are different, these points P and Q are different. They are not the same point. All right. Suppose we want to compute the distance between these 2 points. So I want to find the length of this line segment that contains these two points. To do so, we can build a right triangle. So I can bring a horizontal from point P over to here, and then connect it up with a vertical that goes up to point Q. And ladies and gentlemen, in order to find the distance between these points here, the distance of this line segment, we realize that it is the longest side of the right triangle opposite my 90-degree angle, which is right here. This is my 90-degree angle or right angle. And the longest side of a right triangle is called the hypotenuse. So to find the length of this hypotenuse is equivalent to finding the distance between these points. To do so, we would tap into the Pythagorean theorem. The Pythagorean relationship's been around for thousands of years, and basically it says this: given any right triangle, and of course to be a right triangle, a triangle has to have a right angle in it, which means a 90-degree angle in it. So given any right triangle, the length of the longest side, which I'll call side C, relates to the lengths of the two shorter sides of the triangle. These two shorter sides are called the legs of the right triangle. The longest side of the right triangle, opposite the 90-degree angle or the right angle, is always referred to as the hypotenuse. Pythagoras, a mathematician back in BC time, thousands of years ago, discovered that if you take the length of the longest side of a right triangle and square its length, it's always equal to the sum of the squares of the lengths of the two legs of the right triangle. This is called the Pythagorean relationship, or the Pythagorean theorem in mathematics, in honor of the individual who discovered this many, many moons ago. Okay. All right. So that's how we would find a missing side. Given two of the three sides of our right triangle, we should be able to find the third missing side. So if we were given the two legs and we were asked to find the length of the hypotenuse, we would take the positive square root of both sides of this equation to solve for the length of the hypotenuse. If we were given the length of the hypotenuse and the length of one of our legs to find the other leg, say we were not given leg A here, we would have to find it by taking the square root of the length of the hypotenuse squared minus the known leg length. That's how we would find the length of our other missing leg there. Okay. So we're going to employ this Pythagorean theorem here to finding the distance between 2 points in the plane. And so what is the length of this leg of a right triangle? Well, that's just going to be nothing more than the difference between the x coordinates of these 2 points. So x sub 2, which would be here on the x-axis, minus x sub 1, which would be right here. This length here is the length of this leg. And so if you take the difference between the x coordinates and take the absolute value of the difference to ensure that the difference is positive, you'll have the distance between this point here and this point here. In other words, you'll have the length of this leg of our right triangle. In a similar fashion, if you project this point back to the y-axis, it strikes y2. And if you project this point horizontally back to the y-axis, it strikes y1. The length of this leg of our right triangle is going to be the absolute value of the difference between the y coordinates of these two endpoints here. And then, therefore, to find the length of the hypotenuse, which is labeled D, we would subject these known lengths to the Pythagorean theorem. And so, ladies and gentlemen, we can derive what is called the distance formula. So therefore, the distance between any 2 points, x1, y1, and x2, y2 in the plane can be found by using this formula called the distance formula, where you take the positive square root of the sum of the squares of the differences between the coordinates of the endpoints. Okay? And that's your distance formula. That will always compute the distance between any 2 points in the xy plane. All right. And why did we drop the absolute value symbols around these differences? Well, because we don't need them. Because when you square a difference, it's always going to come out as a positive. So we don't really care if this difference is positive or negative anymore, because we're squaring the difference anyways. All right, so that's called the distance formula. So this is a formula that you either want to commit to memory or, have handy on a note card, enabling you to compute the distance between any 2 points in the plane. All right, any questions about that there? All right, so let's put it to work here. Suppose we want to compute the distance. between these 2 points in the plane, and my 2 points are going to be -5, 1. And my other point is going to be 7, -3. So therefore, to find the distance between these 2 points, I'll call D. It's going to be the positive square root of the sum of the squares of the differences between the coordinates of these points. Suppose I call this point my first point, x1, y1, and designate this as being my second point. By the way, it doesn't matter which one you call your first and second point. So the distance between these 2 points in the plane is going to be the positive square root of 7 subtract a -5 squared plus -3 subtract 1 squared. Therefore, the distance between these 2 points is going to be positive square root of 7 minus a -5, which is 7 plus 5, which is 12. So 12 squared plus -3 minus 1 is -4 squared, which is going to be 16. Excuse me, which will be 4 squared, -4 squared, rather. All right, so we're going to have the square root of 144 plus 16. And that's going to net us the square root of what? 160, square root of 160. And that'll be the distance between these 2 points in the XY plane. Now, if you want to turn that into a decimal to appreciate that distance, you would take the square root of 160. And the square root of 160 nets me a distance of about 12.6 units. So about 12.6 units would be the distance between these 2 points in the XY plane. Any questions how I applied the distance formula to computing the distance between those 2 points? Essentially, that's it there.
In our answer, do we need to put like 12.6D or anything, or just the number?
You could just put 12.6 for the distance, or you could leave it as a square root of 160. Now, the square root of 160 does simplify, though, correct? The square root of 160 would simplify to what? Well, 160 is rewritable as 16 times 10, and the square root of 16 brings the 16 out as a 4. So this simplifies down to 4 times the square root of 10, correct? In exact form, that would be the distance between those 2 points. So approximate distance would be about 12.6. So exact answer, exact distance, approximate distance. All right. All right, so it just depends what I would be asking for as to what form I would like to have it reported as. All right, now another thing is I want to look at is something called the midpoint formula. How would we compute the midpoint between any 2 points in the plane? So we're going to develop a formula called the midpoint formula. We already seen the distance formula. So suppose that we have 2 points in the plane. I'll call this point x1, y1, designate this one as x2, y2. And we want to find the point that's halfway in between these 2 points. We want to find what's called the midpoint. All right, so how would we find this midpoint here? Well, if I drop this perpendicularly down to the x-axis here, I would strike the tick mark of x1. If I drop this perpendicular down the x-axis, I strike the tick mark x2. All right, that makes sense so far here. And if I bring this point back to the y-axis, I strike the tick mark y1. And I bring this back to the y-axis, I strike y2. All right, so what's the midpoint? The point halfway in between these 2 points here? Well, the x-coordinate of the midpoint is going to be basically the middle value between x1 and x2. And so to find the middle value between x1 and x2 is to find the average of these 2 values, if you will. And so to find this value, we will add the x and x coordinates together. And then we're going to divide by 2. So this will be the value that's halfway in between x1 and x2. This, therefore, would be the x coordinate of my midpoint up here. in a similar fashion to finding the y coordinate of my midpoint, it's going to be the halfway value in between y1 and y2, which is going to be found by taking the average of y1 and y2. So therefore, the midpoint, what is the ordered pair address of the midpoint? Well, the x coordinate of the midpoint is going to be the average of the x coordinates of the two endpoints of this line segment. So x1 plus x2 divided by 2. The y coordinate is going to be the average of the y coordinates of these 2 points, y1 plus y2 divided by 2. So this is called your midpoint formula. Given 2 points in the xy plane, you should be able to use it to compute the ordered pair that represents the midpoint, halfway in between the points x1 and y1 and x2, y2. So that's another important formula there to lock away in the memory bank, called the midpoint formula. Any questions about that derivation there? All right, well, let's see if we can use this formula. So here's a typical problem. Find the midpoint between, give you a couple of points to work with here. Negative 1.5 and negative 9 and the point negative 8.7 and 4. All right, so to find the midpoint between these 2 points, maybe we can call this our point x1, y1 and designate this as our second point. Or you could have them switched around. All right, so the midpoint between these 2 points, the x coordinate is going to be the average of these x coordinates here. So negative 1.5 added to negative 8.7 divided by 2 will be the x coordinate of the midpoint. The y coordinate is going to be the average or the middle value between negative 9 and 4. So we add negative 9 and 4 together and divide by 2. Now negative 1.5 added to negative 8.7 is going to net us what? Negative 10.2, I believe. And negative 9 plus 4 is negative 5. So the midpoint, the point halfway in between these 2 points, is going to be negative 5.1 for the x coordinate, and the y coordinate would be negative 2.5. And that would be our midpoint. So that is the midpoint between these 2 points here. Any questions how I applied the midpoint formula there? So 2 formulas we have learned here so far. That being the what? The distance formula and also the midpoint formula. All righty. Any questions about any of this here? Okay. All right, now another thing that we do, probably a little bit more importantly in the XY plane, is besides plotting points, we also like to graph relations or functions in the XY plane. Okay. And there's many ways to graph functions or relations. But most notably, the first method that you usually encounter in early algebra to graph a equation in 2 variables is to use what's called the table method. So we will try to graph this this function or a relation here using the table method. So as the name suggests, we're going to make a table here. This is going to be called my X column. And then my other column to the right of that, I'm going to label as being my Y column. Okay. And then I always like to have a column which represents my ordered pair, X comma Y. Now, ladies and gentlemen, you can choose any values for X, but whatever you choose for X, it has to go into the equation in order to solve Y for Y. You might want to, try to keep the values or choices for X close to the origin. I mean, you don't want to choose like a value for X that might be something like a million. Because if you choose 1,000,000 for X, trying to plot that point is going to be virtually impossible. Okay. So what would be some nice values for X? And don't just try positive values, try some negative values too. All right, so I'm going to try maybe like -2, -1, 0, 1, and 2. Okay. All right, so I'm going to let X take on these values, and then I'm going to have to therefore compute what Y would be for each of these values. So if X is equal to -2, I put -2 into my equation, and therefore I have to solve for Y. So we're going to have 4 plus Y equals 4. Subtracting 4 from both sides implies that Y is equal to 0. So therefore, -2, 0 is going to be a point that lies on the graph of this equation in X and Y. Does anybody recognize the fact that this point also qualifies as being what is called a what? A y-intercept. I don't know if that rings a bell or not. It's a point of intersection between the graph of this equation and the y-axis. That's not right. I have that wrong. It's the x-intercept. All right, so this is an x-intercept because this is a point that lies on the x-axis. So it's a point of intersection between the graph of this equation and the x-axis. All right, if X is equal to -1, what would Y be? To find out, put -1 in for X and go ahead and solve for Y. So we're going to have 1 plus Y equals 4. Therefore, Y is equal to 3. So -1, 3 is yet another point that would lie on the graph of this equation. If X is equal to 0, what's Y going to be? Put 0 in for X, solve for Y, and therefore we discover that Y would just be equal to 4. This is a point that also lies on the graph of that equation. By the way, this point lies on the y-axis, and it would be a point of intersection between the graph of this equation and the y-axis. So this would be called a y-intercept. If X is equal to 1, we put 1 in here. 1 squared is 1, and we'll have 1 plus Y equals 4. Solving for Y, we subtract 1 from both sides, and we get Y is equal to 3. Yet another point that lies on the graph of this equation. Finally, if X is equal to 2, we put 2 in for X here. And then we're going to solve for Y. We get 4 plus Y equals 4. Subtracting 4 from both sides, we get Y equals 0. And so we can see that another x-intercept here would be 2, 0. This is also an x-intercept. All right, I have a question. Do you think we have enough points here computed to accurately discern what the graph of this thing looks like? Now, ladies and gentlemen, we're going to get some graphing paper here, and I will attach a piece of graphing paper to Canvas so you can copy it off and print it off, copy it off if you want, or you can even make graphing paper or download it from free sites online, or you can just buy a tablet of graphing paper at an office outlet. It's usually not that expensive. But whenever we graph, we always like to use graphing papers so that we are accurate and neat. All right, so I will call this my x-axis and label this as being my y-axis here. And we're going to plot these points. So to plot the point -2, 0. Start at the origin. I'll move 2 to the left on the x-axis. -1, -2. There's -2, 0. And, if you want to, if you want to label the points, you can do that. You don't have to label them. Because the labeling does clutter up the graph, but I'll see if I can sneak the ordered pairs next to them. There's -2, 0. Plotting the point -1, 3. We start at the origin. We go 1 to the left and then up 3. 1, 2, 3. There's -1, 3. Plotting the point 0, 4. We start at the origin and we don't go right or left. We just go up 4. 1, 2, 3, 4. Right here on the y-axis. There's the point 0, 4. Plotting the point 1, 3, we start at the origin, move 1 to the right, then up 3. 1 to the right, up 3. 1, 2, 3. There's 1, 3. And plotting 2, 0. Start at the origin, move 2 to the right on the x-axis, and stay on the x-axis. 2, 0. All right, I think we can kind of see that the graph of this equation involving x and y is going to be a curve type graph, and we'll start fitting it to the points we plotted. And you can see that it looks like this graph is going to look like this, correct? All right. This graph has a name. It's called a parabola. And this parabola, we say, opens downwards. Okay. And all quadratic functions, because this is a quadratic function in x and y, generate parabolic graphs. So we're not surprised there. But that would be the graph of this equation, x squared plus y equals 4. Any questions how I graph that equation using the table method and generating ordered pair solutions here? And then plotting the points and then connecting them with the curve. All right. All right. Any questions? All right, maybe we could try another one, huh? Let's see if we can sneak this in down here. We'll try to graph y squared minus 1 equals x. We will try to graph this equation. We'll use the table method. And we need to choose some nice values for x. Some nice values of x. Well, I'll tell you what, let's see here. Actually, ladies and gentlemen, by inspection of this equation here, it might be easier to choose values for y and compute what x is. Reason being is if we choose values for x, we're going to have to solve for y, and we're going to ultimately have to take the square root of both sides. Do you agree? Which is going to be kind of nasty. So why don't we choose values for y here? All right, let's choose like, I don't know, maybe -2, -1, 0, 1, 2. Let's choose those values for y. Now we have to compute what x would be. So if y is equal to -2, I'll plug -2 in for y, and then we're going to solve for x. So we'll have 4 minus 1 is equal to x, which implies x equals 3. Hence, the ordered pair 3, -2 is not only a solution to this equation, but it's a point that would also lie on the graph of that equation. If y is equal to -1, we substitute in -1 in for y, and we would have -1 squared minus 1 equals x. So we're going to have 1 minus 1 equals x, which means x is 0. Hence, the ordered pair 0 and -1 also is a point that lies on this graph. If y is 0, we put 0 in for y, and what would x be? 0 squared minus 1 is equal to x, which means x will be equal to -1. Another point that would lie on the graph of that function there. This is not a function. That would lie on the graph of this equation here. This is just a relation. We'll find out in the next section. Now we're going to let y be 1. Take 1, substitute it in for y. We'll have 1 squared minus 1 equals x. In which case we got 1 minus 1 equals x. So x is equal to 0. Finally, if y is equal to 2, to find x, we put 2 in for y in the equation and solve for x. So we're going to have 2 squared minus 1 equals x, which implies that x is equal to 4 minus 1, which is equal to 3. And there you have it. We can now plot those points in the xy plane, connect them with the curve, and we'll have the graph of that equation in x and y. Any questions how I generated those ordered pair solutions? All right, so take a piece of graphing paper. Always label your axes, very important, so the reader knows what they pertain to, because graphs are often applied to the sciences and engineering applications, in which case it's critical you label your axes. Otherwise, we're not going to have a clue what they pertain to. Okay. All right. It's also a good thing maybe to label a couple of tick marks on both axes to establish the scaling or the scale that's being used. Okay. These tick marks are spaced 1 unit apart on both axes. All right, plotting these points. To plot the point -2, 0. Wrong. It's this one right here. I'm sorry. To plot the point 3, -2. We start at the origin, and I move 3 to the right on the x-axis, 1, 2, 3, and then down 2, -1, -2. So there's the point 3, -2. Plotting the point 0, -1, we start at the origin, and I move down 1 unit on the y-axis. There's 0, -1. Plotting the point -1, 0, we start at the origin, move 1 to the left, and then stay on the x-axis. So -1, 0 is going to be right here. And then plotting 0, 1, we start at the origin and move up 1 unit on the y-axis, and then we stay on the y-axis. There's 0, 1. All right, plotting 3, 2, we start at the origin, move 3 to the right, and then up 2. 1, 2, 3, now up 2, 1, 2. There's the point 3, 2. And I think we plotted enough points to see what kind of a graph this is going to generate. It's going to be like a curve type graph, or kind of like a parabola that opens not upwards or downwards, but this parabola opens actually to the right. Okay, so that would be the graph of y² - 1 = x. Everybody see that there? All right, so that would be the graph of that equation there. All right, so the table method is a very popular way to graph an equation in x and y. Just by finding some ordered pair solutions that satisfy the equation and plotting them, you'll start to see what the graph looks like. Any questions about that there? Okay. All right, another thing that we're often very concerned with, ladies and gentlemen, when working with graphs of equations in x and y is the x and y intercept of the graph. So let's review for ourselves what x and y intercepts are. Suppose I have the graph of a linear function and it generates this line graph. The point of intersection between the graph and the y-axis, this point has a very special name. It's called the y-intercept of the linear function or the graph. It marks the point of intersection between the graph and the y-axis. Notice, in order to be a y-intercept, a point has to lie on the y-axis. And any point that lies on the y-axis must always have an x-coordinate that's equal to what? What do you think the x-coordinate has to be for a y-intercept if it's to be a point on the y-axis?
0.
0. Because if the x-coordinate is not 0, then the point will not be on the y-axis. It's going to be to the right or to the left of the y-axis. In a similar fashion, the point of intersection between the graph and the x-axis is a very important point. It's called the x-intercept of the graph. And since an x-intercept is a point of intersection between the graph and the x-axis, it must lie on the x-axis. And in order for any point to lie on the x-axis, the y-coordinate must always be equal to 0. True? So this not only shows us what the intercepts are, but it shows us how to find an x and y intercept. To find an x-intercept, we always set y equal to 0. To find the y-intercept, we always let x be 0. All right, let's put this into practice. Suppose I want to find the x and y intercept. Of the equation y = x² - 4. All right, so how would I find the x and y intercept for this equation? Well, let's find the x-intercept first. To find the x-intercept, what do I set equal to 0? Y. Easy way to remember this is just remember, to find an intercept, you always set the other variable equal to 0. So to find the x-intercept, we set y equal to 0. To find the y-intercept, we set x equal to 0. All right, so to find the x-intercept, we let y be 0, replace y in the equation with 0, and now we're having to solve a quadratic equation. So how do we solve this quadratic equation for x? We've seen many ways to solve these equations. We've seen the factoring method, the square root method, the completing the square method, and also the quadratic formula method. What would be the quickest, most efficient way to solve this quadratic equation for its two solutions? Anybody? What would be the quickest way? Well, probably the quickest way here would be using the square root method or the factoring method. This is the difference between the squares, so it does factor in x minus 2 times x plus 2. Setting these factors equal to 0 and solving for x, we discover that we get two x-intercepts. We get positive 2 and we get negative 2. So the two x-intercepts would be 2, 0 and also negative 2, 0. So this equation's graph has two x-intercepts. There they are. These are 2 points where the graph of this equation will intersect the x-axis. To find the y-intercept or seps, what do we set equal to 0 always? We always set x equal to 0. Take 0, substitute in for the x variable. The equation becomes y is equal to 0 squared minus 4, which means y is negative 4. Hence, 0, negative 4 is the only y-intercept of the graph of this equation. And therefore, the graph of this equation will only intersect the y-axis at one point, 0, negative 4. Any questions how I cranked out the x and y intercepts for this equation? By the way, if you're interested in knowing what the graph of that thing looks like, if you were to take the time and graph it, you would see that the graph looks like this. So it would be a parabola that opens upwards, and the x-intercepts are negative 2 and 2, and the y-intercept is down here at 0, negative 4. Makes sense. Y-intercept, two x-intercepts. Any questions about what just happened there? Okay. All right, same thing. Let's find the x and y intercepts for, how about this equation? Y equals the absolute value of x minus 1. Well, nothing changes. Still proceed the same way. To find the x-intercept, we're going to let y be 0. Set y equal to 0, and now we have to solve this absolute value equation. To solve this absolute value equation, we want to isolate the absolute value, so we add 1 to both sides, and we have the absolute value of x is equal to 1. Dropping the absolute value symbols, we see therefore that x has to be equal to positive 1, or x equals what? Negative 1. So we have two x-intercepts, 1, 0, and negative 1, 0. Those are the two x-intercepts. Finding the y-intercept, we set x equal to 0. Take 0, substitute in for the x variable, and y is equal to the absolute value of 0 minus 1. Y is equal to 0 minus 1. Y is equal to negative 1. So my y-intercept is 0, negative 1. That's my y-intercept. Just out of curiosity, if you were to take the time and graph this absolute value equation or function, we would see that the graph would be a V-shaped graph opening upwards. And there's going to be two x-intercepts, negative 1 and positive 1. It's two x-intercepts. And then you have a y-intercept, which is at 0, negative 1 down here. That's your y-intercept. Is this making any sense here? All right. Now, I've shown you manually how to crank out X and Y intercepts for an equation in X and Y. We can also use our calculator, ladies and gentlemen, to help us find X and Y intercepts, our graphing calculator. And I wanted to show you that quickly if I could. So go off and get our graphing calculator here. Hold on a second, I gotta make sure I have an appropriate background here so that we can see the calculator. Oh, okay. All right, so I'm going to open up Microsoft Word because I want a white background here. Okay. All right, so let's go look at our graphing calculator here. So what we're going to do is we're going to, let's see, we need an equation here. And let's use y equals x squared minus 4, the one we found our x and y intercepts to be negative 2, 0, 2, 0, and 0, 4. Oops, x squared. Did I say x squared minus 4? Yeah. Okay. Y intercept would be 0, negative 4. All right. Anyways, you get your y equals button to type in the equation you wish to graph, and your equation has to be solved for y in terms of x. So if I want to graph y is equal to x squared minus 4, I would hit my x button right here. This is your x button, and you want to square this. I'll raise to the second power, subtract 4. And I should be able to graph this function here. If you hit the graph button now, you may or may not see it depending upon how your axes are scaled. But there would be the graph of my parabola opening upwards. If I hit my window button up here on the top of the keyboard, we have a button that says window. You can see how my x and y axis are configured. My x-axis ranges from negative 10 to 10, where the tick marks are spaced 1 unit apart. The y-axis ranges from negative 10 to 10, where the tick marks are also spaced 1 unit apart. So this tick mark on the x-axis way over here to the left is negative 10. The one on the extreme right of the x-axis is positive 10. And my x-axis runs from negative 10 to 10 by 1, where the tick marks are spaced 1 unit apart. Y-axis runs also from negative 10 to positive 10, where tick marks are spaced 1 unit apart. All right. Do we all see that graph on our calculator? All right, now I'm going to show you how to find x-intercepts. Find x-intercepts on your graphing calculator. Once you have your equation graphed, you're going to go to your calculate mode. So above your trace button, it says calculate, calc. So we have to hit our second button followed by the trace button to get into calculate with the graph showing. So second, trace, and we want to go down and use the 0 function. The 0 function is the function that we use always to find zeros or x-intercepts. We'll learn later on in this course that the name of an the words x-intercept and 0 are synonymous with each other. They mean the same value. All right, so to find the x-intercepts, we always use a 0 function. Hit enter to activate the function. You'll see your graph reappear, and you'll see a blinking cursor somewhere on your graph. If I want to find this x-intercept over here to the left, I'm going to have to navigate my blinking cursor in this vicinity. Notice my calculator wants to box in this x-intercept so that it can find the x-intercept using a numerical routine behind the scenes. By virtue of the way my graph slants and going through the x-axis at negative 2, I'm going to call a point above the x-axis on the graph as being a left bound, because this graph projects vertically down to the x-axis. That's to the left of our x-intercept we wish to find. We'll call that a left bound by hitting enter. Now your calculator wants us to establish a right bound. So to do that, we navigate the blinking cursor a little bit below the x-axis by hitting the right arrow key. Somewhere in here. This will be called a right bound because it projects vertically up to the x-axis at a point that's to the right of the x-intercept we wish to find. Hit enter. That's called a right bound. So your calculator essentially has boxed in your x-intercept that we wish to find. And your calculator needs to do this. It's part of its routine that it goes through to find the x-intercept. When your calculator says guess, just hit the enter button again. And you can see that one x-intercept is -20. That's one x-intercept. To find the other x-intercept over here, we go back to calculate. Go down and use the 0 function again, but this time we have to navigate our blinking cursor in the vicinity of the other x-intercept over here. A left bound is going to have my cursor be below the x-axis in this case by virtue of the way the graph slants as it goes through the x-axis at our x-intercept. Because this cursor projects up to the x-axis, that's to the left of the x-intercept. That's why we call it a left bound. Now your calculator wants a right bound, which means we have to navigate the blinking cursor a little bit above the x-axis. Because this blinking cursor now projects straight down to the x-axis at a value that's to the right of the x-intercept we want to find. So hit enter. Now your calculator says guess. We just hit enter again, and there's your other x-intercept 20. Finally, to find the y-intercept, which is down here, if you're not able to visually read it off precisely, you are welcome to go to calculate, second trace. And this time go down, rather in this case, just use the value function. So the value function finds y-intercepts. The 0 function always finds x-intercepts. All right, so we're going to evoke the value function. And in order to find the y-intercept, we always set x equal to what? What do I set x equal to?
Zero.
Yeah, you are correct. So I'm going to set it equal to 0, hit enter, and there's your y-intercept, 0, -4. Any questions how, given a graph, how we find the x and y-intercepts on the graph using our utility and calculate? Either the 0 function to find x-intercepts or the value function to find y-intercepts. Okay? Any questions? All right. Okie dokie. All right. The only thing I want to concern ourselves with in section 2.2, as notice it's really not on the schedule, is the equation of a circle. Okay. So in passing over section 2.2, I just want to pick up one thing out of it. The equation of a circle. Suppose I have a circle that's graphed in the first quadrant of the XY plane. And circles are always characterized by a center point and also characterized by a radius that emanates from the center point and touches a point on the graph, on the circle somewhere. This is called a radius. All right. Suppose the ordered pair address for my center is the ordered pair HK. You're probably wondering what's up with the HK. Why not just call it XY? Well, the convention in mathematics when talking about conic sections, hyperbolas, parabolas, ellipses, and circles is to call the center point HK. So I'm just following the notation used in textbooks. So therefore, if the center point of this circle is HK and the radius has a length of r units, then the equation of this circle is going to be this. It's going to be x minus h quantity squared plus y minus k quantity squared equal to the radius squared. So there you have it, ladies and gentlemen. That is the equation for a circle that is centered at HK and has a radius of length r units. That is the equation of a circle. Notice both the x and the y variables are squared. But that is the equation that would generate a circle that's centered at HK and also has a radius of R. Okay, so knowing that, suppose I have us do this one problem here. Write the equation of a circle centered at 5, -4. And suppose that the circle has a radius of R equal to 9. Okay. Well, this is our center point, so that's going to be HK. That's your point HK. So H is 5 and K is -4. So dropping things into our equation formula for a circle, we're going to have x minus h, x minus 5, quantity squared, plus y minus a -4. -4 drops in for k squared, equal to your radius squared. Your radius is 9, so we got a square radius. Therefore, the equation of this circle in simplified form is x minus 5 squared plus y plus 4 squared. 9 times 9 is 81. And there you go. That would be the equation of the circle that has this center and has this radius here. And, you know, if you were to plot this circle here, the center is at 5, -4. So the center is down here in the 4th quadrant. And the radius is 9 units in length. So you have to go 9 units this way, 9 units this way, 9 units this way, 9 units this way, 9 units in either all directions. Connect these points, and you would have the graph of that circle that's centered at 5, -4, and the radius would have a length of 9 units. Okay. All right, so that's about all I want to involve ourselves in a circle. One more thing with the circle is, if you're not given a radius, but you're given the diameter of a circle, how does a diameter relate to the radius of a circle? Anybody? The diameter of a circle is, this is called the diameter, and this is just called the radius. So a diameter is always 2 times the radius, or the radius is half the length of a diameter. Okay. Is that making any sense to you? So diameter is always twice the length of a radius, or a radius is always half the length of a diameter. All right, find the equation of a circle whose diameter has endpoints -1, 0, and 3, 4. All right, so therefore, we want to write the equation of a circle whose diameter contains these 2 endpoints here. We want to write the equation of the circle. Well, we're not given a radius now, we're given the diameter. And the equation of a circle is x minus h quantity squared plus y minus k quantity squared is equal to r squared. Where the center point is going to be hk, and the radius is r. First of all, we're going to have to find the radius. And the radius is going to be half the length of our diameter. But how do we find the length of our diameter? We're going to have to use the distance formula. So we're going to call this point x1, y1. We're going to call this x2, y2. So the diameter has a length of what? It's going to be the square root, using these 2 points, of the square of the difference between the x coordinates. So 3 minus a negative 1 squared, plus the square of the difference between the y coordinates, 4 minus 0. Therefore, our diameter is going to be 3 minus a negative 1, which is 4. 4 squared is going to be 16. And 4 squared is 16. So the diameter is going to be the square root of 32, which is really the square root of 16 times 2. Square root of 16 comes out, brings the 16 out as a 4. So we got 4 root 2. So that would be the diameter. That's the length of the diameter. 4 times the square root of 2 units in length. That's the length of this diameter. But we need the length of the radius. Well, how does the radius compare to the diameter? Well, the radius is 1/2 of the diameter. So basically, we're going to take the diameter, which is 4 root 2, and divide it by 2. That gives us, this reduces down to 2. So 2 root 2 is the length of the radius. That's r. That's the length of the radius. From here to here, that's the radius. Another thing we're going to need to know, not only is the radius, but we're going to need to know the center of the circle. Well, the center is the midpoint of the diameter. And so we got to find the midpoint between these 2 points here using the midpoint formula. So the center is going to be the midpoint between these 2 endpoints of our diameter. So the x coordinate of our center point is going to be the average of the x coordinates of the 2 endpoints of the diameter. That's the same, negative 1 plus 3 divided by 2, 0 plus 4 divided by 2. So therefore, this is going to be negative 1 plus 3, or 2 over 2. This is going to be 4 over 2. So our center point is going to be 1, 2. That's what HK is. All right, we're ready to write our equation of our circle. We know enough about it now, so we just fit things into our equation of our circle. So we have x minus h. What's h? H is 1. Plus y minus k. What's k? K is 2. Equal to our radius squared. Our radius is 2 root 2. And that has to be squared. This would be the equation of your circle. In simplified form, it'd be x minus 1 squared plus y minus 2 squared. And 2 root 2 times itself is going to net us 2 times 2 is 4. And root 2 times root 2 is 2. So we're going to have 4 times 2 or 8. Ladies and gentlemen, this would be the equation of that circle there. That has this for its diameter. Okay, everybody understand how, given the diameter endpoints of the circle, we were able to write the equation of the circle.
I have a question.
Yep, go ahead.
So how did you, so with diameter, did you use the distance formula?
Yeah, I found the length of my diameter by finding the distance between these 2 points here.
Okay.
So I fed things in to the distance formula. And the distance formula says, again, we take the positive square root of the sum of the differences, sum of the squares of the differences between the coordinates. So I take the square of the difference of the x coordinates, 3 minus a negative 1, plus the square of the difference of the y coordinates, 4 minus 0. All right. And then I got my diameter, and then I just took half of my diameter to generate my radius, because the radius is always half a diameter. All right. And then I use the midpoint formula to find the center point between the two endpoints of my diameter. The center point is the midpoint. And then I fed things into my equation of my circle. Right, the equation of this circle. Any other questions about this problem? All right. All right. If I give you this equation for a circle here, can you tell me what the center of the circle will be and what the radius would be? What would be the center of this circle? What would be the center? What's the ordered pair that represents the center of this circle here? My H would be 3/2. That's the X coordinate of my center point. My K would be not positive 3/4, but negative 3/4. The reason being is because I got a positive here. The equation of a circle requires I have a minus. So Y plus 3/4 would have to be rewritten as Y minus a negative 3/4. And therefore my Y coordinate of my center point is negative 3/4. That would be the center point of the circle. The radius of the circle is going to be the square root of 81/49, which is going to net us 9/7. That would be the radius, 9/7. Any questions how I found the center and the radius of this circle here? Easy way to remember it is the coordinate of your center point is always has the opposite sign of what this is. So if this is a minus sign, that's why our X coordinate is positive. This is a positive sign. That's why our Y coordinate is negative. Okay. All right, any other questions about circles there? That's about all I want to say about circles. And that brings us to the last section today, section 2.3. So in section 2.3, we're going to introduce ourselves to functions and relations in mathematics. We're also going to look at something called the domain and range of a function or relation. Okay, so section 2.3. Just like people have relations, well, in mathematics, we have relations too. What is a relation? What's the definition of a relation? The definition of a relation is it's nothing more than it's just a set of ordered pairs. What's a function? A function is a relation in which no two different ordered pairs have the same X coordinates. So in order for a relation to be a function, all the X coordinates have to be unique. All right, let's look at this set of ordered pairs here. This is called an open brace. 3, 1, 2, 5, negative 4, 2, negative 1, 0, and 3, negative 4. This is obviously a relation because it's a set of ordered pairs. But is it a function? Is this a function?
No,
Okay, you're saying no, it's not. Why not?
there are 2 3s in the axis.
All right, so we do have two different ordered pairs in this relation that possess the same X coordinate. We don't care if we have duplicate y coordinates. It's only if we have duplicate x coordinates. So notice these two different ordered pairs here do have the same x coordinates. And because of that, this is not a function. It's only a relation. So this is just a relation, not a function. All right, let's look at this set of ordered pairs. So obviously, being a set of ordered pairs, it is a relation. But does this relation qualify as being a function? All right, here we have another relation, a set of ordered pairs. Is this relation a function? I see two different ordered pairs with the same y coordinates, but do we care about duplicate y coordinates? The answer is no. Are all my x coordinates unique? Are they all different? The answer is yes. So this Lezman is not only a relation, it's also a function. So this is an example of a function. All right. I'm going to call this relation here relation f. I'm going to call this function, this relation or and function, I'm going to call it g. All right, now there's two very important sets that we often concern ourselves with when working with relations or functions in mathematics. The first set is called the domain. What's a domain? A domain of a relation or a function is nothing more than the set of all x coordinates of a relation and or function. The range, what's the range of a relation or a function? A range is the set of all y coordinates of a relation and or function. All right. Oh, another note in passing, all functions are relations, but are all relations functions? All functions are relations, but are all relations functions? The answer is no. All right, let's go back to our relation up here. What would be the domain of our relation f? Notice the notation, D for domain, domain of relation f. Well, the domain consists of all the x coordinates. So what would be all the x coordinates of all the ordered pairs that define this relation? And normally, but this is not really critical, but normally we like to list the x and y coordinates in descending order from left to right on our paper. So therefore, all the x coordinates for this relation that belong in its domain would be -4, -1, 2, and 3. Notice, just because we got duplicate x coordinates, we do not have to list these twice in the domain, just list it once. What would be the range of this relation f? It's the set consisting of all y coordinates of all points of the relation. So the range is going to be a set consisting of -4, 0, 1, 2, and 5. That would be the range of relation f. Any questions so far what a domain and range is? All right. What would be the domain of this function g? It would be the set consisting of what? all the x coordinates, -4, -1, 2, 3, 10, and 60. The range would be the set consisting of all y coordinates. 3, 4, 5, and 100. Okay. Relations or functions can be represented by using tables, or even a little diagram like this, where this would be the domain set, this is the range set. So suppose that -4 gets mapped to 2, hence we would have -4, 2 as being one ordered pair in this relation here. -1 gets mapped to 0 by this relation, so -1, 0 is another ordered pair. 2 gets sent to, let's say, 5 down here, so 2, 5, another ordered pair. And let's say 3 gets sent to -4 up here, so 3, -4. So this is certainly a relation. It's a set of ordered pairs. What would be the domain of this relation? And by the way, is this relation a function? Do we see more than one arrow emanating from any value in the domain? The answer is no. So we do not have any duplicate x coordinates. All the x coordinates are unique. So this is a function. What would be the domain? The domain is a set of all x coordinates of this function here. So that would be -4, -1, 2, and 3. That's the domain. What's the range? The range is a set of all y coordinates of this function, which would be -4, 0, 1, 2, 5. That would be the domain and range. Any questions about what a relation is, what a function is, what the domain, and what the range of a relation and or function is? All right, but oftentimes, ladies and gentlemen, relations and functions are not handed to us as a set of finite number of ordered pairs. Oftentimes, we have to deal with the graph of relations or functions. And how would we determine by looking at the graph whether our relation qualifies as being a function? Well, we have a test. It's called the vertical line test. The vertical line test can be administered, abbreviated as VLT. The vertical line test can tell us whether the graph of a relation is a function. That's what it's designed to tell us. And how does the old vertical line test work? Well, this is how it works. Suppose I have the graph of a relation in the XY plane. Suppose the graph looks like this. This is certainly a relation because it is a set of ordered pairs. In fact, how many ordered pairs or points sit on this graph? How many points sit on this graph? There's an infinite number of them. So it's certainly a relation. But is it a function? Well, to find out, we take a hypothetical vertical line. And if I can place a vertical line somewhere in the XY plane such that it hits the graph in more than one point, then my relation is not a function. So notice I could position a vertical line right here, and it would go through my graph in more than one point, or touch the graph in more than one point. Because of that, we would see that there would be two different points on this graph that have the same x coordinate. Therefore, this is not a function. We say the graph fails the vertical line test. Not a function. because we can place a vertical line somewhere in the XY plane and have it hit the graph at more than one point. That's not a function. It's a relation, but it's not a function. All right, suppose we have the graph of another relation, and suppose it looks like this. It's a relation, it's a set of ordered pairs, but is it a function? If I take a hypothetical vertical line and place it anywhere in the XY plane, I don't care where you put it, anywhere. Notice a vertical line would only touch this graph and at most one point anywhere, no matter where you put the vertical line. And because a vertical line placed anywhere in the XY plane touches this graph and at most one point anywhere, this is also a function. We say the graph passes the vertical line test. Passes the vertical line test. So, ladies and gentlemen, is this making any sense what the vertical line test can tell us about whether the graph of a relation qualifies as being a function or not? Okay. This is not. Is this relation here a function? If you put a vertical line anywhere in the XY plane, does it touch the graph and at most one point anywhere? The answer is yes. So this is an example of a function. Function. And obviously being a function, it's a relation. Is this relation a function?
No.
The answer is no, because you can put a vertical line somewhere in the XY plane and strike the graph at more than one point. Certainly, it is not a function because we have more than one or more than two different ordered pairs with the same x coordinates somewhere. So this is not a function. Do we understand the vertical line test? This is not a function. Just a relation, not a function. This one is not only a relation, but it's also a function. All right, so hopefully you understand the vertical line test. It's a very simple test to administer. Very easy test to administer, not difficult at all. Look at the graph of this relation here. This is a relation, ladies and gentlemen. It's the graph of a it's a set of ordered pairs. Is this relation a function? Well, could I put a vertical line somewhere in the XY plane and strike this graph at more than one point? Is it possible? Well, some of you are saying, well, what if I put a vertical line through x equals 2? It looks like the vertical line strikes the graph at more than one point, here and here. But actually it doesn't, because this is an open circle here. And this open circle means that this point 2,5 would not actually lie on the graph. It's not a point that actually sits on the graph. It's an open circle. But this point here, 2,3, being a closed circle, does sit on the graph. So a vertical line placed right here through x equals 2 only strikes the graph at most one point right here. So this is a function. That would be a function. Now, if I close this open circle, would it be a function then? Would it be a function now? Now it's not a function because I could put a vertical line through x equals 2 and strike the graph at more than one point. Now it would be not a function. Are we clear on this? All right, so the vertical line test can help us determine whether a graph of a relation qualifies as being a function or not. All right, ladies and gentlemen, another way to represent relations or functions is by using an equation. If I have y is equal to x plus 1, this is an equation in two variables, x and y. If I was to take the time to graph this equation by maybe using my table method here, generating some ordered pair solutions by choosing some values for x. Suppose I let x be 1. Suppose I let it be like 2. What would y be if x is 1? If y is 1, excuse me, if x is 1, y would be equal to 1 plus 1 or 2. So the ordered pair of 0.12 would lie on the graph of this function here. Ooh, I gave it away. I wasn't supposed to use that word yet. If I let x be 2, if I put 2 in for x, I get y is equal to 2 plus 1 or 3. And we can plot more points. If I let x be 4, I would discover that y was going to be equal to 5. And if you plot these points in the xy plane, you'll discover that you're going to basically get a straight line that goes through these points. And that should not be a surprise because this is a linear relationship that exists between x and y. And the graphs of linear relationships always generate straight line graphs in the xy plane. The linear relationship because both x and y are to the first power. Okay. So if I was to graph this equation by plotting these points here, 1, 2, 2, 3, we're going to discover that we would have a line that looks like this for the graph. Okay, so that would be the graph of this equation y equals x plus 1 here. Well, this is certainly a relation because it's a set of ordered pairs. Is this relation a function? Does the graph pass the vertical line test? The answer is absolutely yes. No matter where you put a vertical line only touches graph and at most 1 point. So this is definitely a function. That's a function. Now, the x variable of this function here oftentimes is called the input variable. Or it's referred to as the independent variable. VBL is going to be short for the word variable. The y variable oftentimes is called the output variable of this function. Or it's often referred to as the dependent variable. Okay. So this is definitely an example of a function. To the right of the equal sign, this x plus 1 is called the definition of this function. It's a rule or a definition that tells us what happens to an input value into this function. It's a rule or definition. So according to how this function is defined, if I put something in for x, the output value is that input value added to 1. You could think of a function as being kind of like a machine in a way. One way to think of a function is to think of it as being kind of like a machine. You throw something into it called x, and this function takes the input value, and according to its definition, it adds 1 to its input value, and then reports out the input plus 1 as the output value. Okay, kind of like a machine. You throw something into the function operates on its input according to its definition and spits something out. Basically what a machine does. It takes some sort of an input, transforms it, and gives you some sort of an output. Right? All right, well, Ladies and gentlemen, instead of calling the output variable y, which is normally the case, in higher level math, oftentimes they use what is called functional notation. Functional notation. Instead of calling y, or the output variable y, oftentimes we call the output variable this guy. And this is to be read as f of x. F of x. You don't say f times x. It's read as f of x. This is called functional notation. It's just another name for y. So you know what? Instead of representing this function as y equals x plus 1, I could represent it as f of x equal to x plus 1. Wait a minute. Do I still have the same function here? Are these still the same functions? Because I changed the name of my output variable from y to f of x, does that change my function? Are we talking about two different functions now, or the same function still? Anybody want to weigh in on it? Are they the same function or different functions? Does changing the name of the output variable necessarily change the function?
No.
You are correct. It does not change the function, because what has not changed? Between here and here, what has not changed? What has not changed, or what has not been altered, is the definition or the rule. The definition of the rule is still the same. We're still adding 1 to the input to generate the output. And because the definition is still the same for this function versus this function, these are identical functions. There's no difference between these functions. The only difference is if you were to graph this function with this notation, you would call the vertical axis not the y-axis anymore. You'd call it the f of x axis. The horizontal axis would still be the x-axis. The graph would still be the same. Still the same graph, because the definition is still the same here as it is here. So basically put, ladies and gentlemen, it does not matter what you call the input and output variable. That's not important. What's important is the definition or the rule that indicates what happens to an input value that characterizes the function, not what you call the input and output variable. Suppose I have a function that's h of t equal to t plus 1. Is this function the same as f of x equal to x plus 1? Is it the same as y equal to x plus 1? Are these functions all the same? Same or different? They are all what? They're all the same function. And they're all the same function because in each case the definition is identical. We keep adding 1 to the input to give us our output value. Because the rule or definition remains the same, we're talking about the same function. No difference between these functions. The only difference is if you were to graph this function using this notation, now the vertical axis would be called the h of t axis, and the horizontal axis would be called the t axis. Same graph, same line, no difference. Same function. It doesn't matter what you call the input and output variable. It's the definition that characterizes your function. Imagination is the limit here. You can get downright silly or imaginative here. I could call my output variable Snoopy of drag, which is really going to be equal to drag plus 1. Got a question for you, ladies and gentlemen. Is this function the same as all these above here? Yes or no? Same function?
Yes.
Same function. Because the definition is still the same. It says we add 1 to the input. Oh, the input's called drag. Who cares? We add 1 to the input to get the output. We add 1 to the input to get the output. We add 1 to the input to get the output. We add 1 to the input to get the output. These are all identical functions. They all have the same graph. The only difference is if we were to graph this one, we would have to call the horizontal axis the drag axis. And the vertical axis would have to be called the Snoopy of drag axis. No difference. Other than that, the graph is the same. So it does not matter what you call the input and output variable of a function. It's the definition that characterizes what a function is all about, not what you call the input and output variables. Okay, so suppose I come up with this one. W of n is equal to n plus 10. Now, is this function here the same as all of these other ones up here? Yes or no? Is this function the same as all these or not?
No,
Oh, why not? Why is it not the same as this one, this one, this one, or this one? What
The
has
number at the end is different.
the definition and the rule has changed? Do you agree? This now has a different rule that tells us something different happens to the input in this function as opposed to these up here. All these rules say we add 1 to the input to get the output. This is a different rule now. It says now we add 10 to the input to generate the output value. Because the rule or the definition is different, this is a different function. It's no longer the same function. And therefore, the graph of this function would not be the same line which is generated by all these other functions. The graph of this function would be more so up here, okay? It would go through the y-axis at 10 as opposed to going through the y-axis at 1. Different graphs because we have a different function. These are different. These functions here are all different from this one. All right. Any questions about the notation surrounding the equation of a function? This gives us a function to play around with. Suppose I have a function defined as g of x is equal to 2x plus 1. And suppose I want you to find g of negative 2. How would we do it? What is this saying to do? To find g of negative 2. That's how we read this. G
Plug in
of
negative 2 for x.
That's right. That's exactly what it's saying. It's saying that we're going to input into this function negative 2. That's the input. The output is going to be g of negative 2. So we're putting negative 2 into, or replacing the input variable in the definition of this function with negative 2. The output there is going to be g of negative 2, which is to say 2 times negative 2 plus 1, which is to say negative 4 plus 1, which is to say negative 3. This is the output. Negative 2 was the input. Therefore, what ordered pair have I generated for this function here? I put in negative 2 and I got out what? I got out negative 3. This would be a point that would have to lie on the graph of this function. One among an infinite number of points that lies on the graph of this function. Suppose I want you to find g of 10. Now we're putting 10 into the function, and the output is going to be g of 10, which is going to be 2 times 10 plus 1, which is going to be 20 plus 1, which is going to be 21. So we generated another ordered pair solution to our function, or another point that would sit on the graph, namely 10, 21. You can throw anything into a function. You can even put a variable into a function. What would be g of a? G of a is going to be 2 times a plus 1. So we put a into our function, and out comes a variable expression called 2a plus 1. You could even throw your dog into this function. I promise you the function does not hurt animals. G of Snoopy. Let's put Snoopy into this function, see what happens to Snoopy. Well, what happens to Snoopy is Snoopy gets doubled, and then we add 1 to that. So out comes 2 times Snoopy plus 1. Put in Snoopy, got out this. Input, output, right? All right. Any questions about that there? Now, we said that the domain and range of a relation or a function is a set of x coordinates and y coordinates respectively. Well, that's great if you have a set of ordered pairs handed to you for the relation or the function. But what if you don't? What if the graph, what if you're given the graph of a function or a relation and you want to determine the domain from the graph? Well, in other words, what if I have the graph of a function and it looks like this in the xy plane? Well, I'll call it the xf of x plane. Use functional rotation. Suppose this point right here is going to be the point -3, -4. And suppose this point right here is the point 10, 10, 3. All right, ladies and gentlemen, we'll call it function f here, function f of x. That's its graph here. So is this relation a function? I've been calling it a function. Well, obviously it must be a function because we can see it does pass the vertical line test, so it is a function. What would be the domain of this function f? Notice the notation, D for domain. Domain of function f. Well, the domain of a function is a set of all x coordinates of all ordered pairs or points that sit on the graph of this function. How many points are on this graph? How many points are on this curve here? There's an infinite number of points on this curve, infinite number. And therefore, there's an infinite number of x coordinates that belong in my domain for this function. Well, if you think I'm going to sit here and enumerate all the infinite x coordinates that lie between -3 and +10, think again. I'll be here till the end of time. So we're not going to do that. In order to represent the domain of this function, we're going to have to use interval notation, which is a popular way of representing the domain. So, ladies and gentlemen, what would be the smallest x coordinate of any point on this graph? The smallest x coordinate that belongs in the domain of this function would be the x coordinate that pertains to the point that's furthest to the left on this graph. And that would be this point right here. And what's this x coordinate? -3. So -3 would be the smallest x coordinate of any x coordinate of any point on this graph. And notice -3, this being a closed circle, means that -3 is to be included in our domain. So we have an open bracket, -3. So my domain goes from -3 up to and includes what value? What's the largest x coordinate of any point found on this graph? The largest x coordinate. 10? So my domain goes from -3 to 10, including the endpoints. That would be the domain of the graph of this function. Just remember, domain always comes from the x-axis. Domain is the set consisting of input values in your function. The range always comes from your y-axis, consisting of the set of all output values of your function. Domain, input, range, output. So what would be the range of this function? Well, what's the smallest y coordinate of any point found on this graph, since the range consists of y coordinates of all points or ordered pairs that define a function or a relation? The smallest y coordinate of any point found on this graph is going to be found in the lowest point on the graph, the lowest point being this point right here. And its y coordinate is -4. So -4 is the smallest y coordinate found in the range, comma, up to, what's the largest y coordinate of any point on this graph? That's going to be the highest point on the graph, whose y coordinate is 3. So the range of this function, okay, goes from -4 up to 3. That's the range. Domain pertains to x coordinate values. Range pertains to y coordinate values. Okay. Any questions how I hammered out the domain and range for that function? The domain and range. All right, let's see if we can go to our textbook here. I bet I have to log in again. It timed me out. All right, I want to go to page 87 and 87 and 96 and go over. No, I want to go to page 194, excuse me. Page 194. And let's see if we can go there quickly here. All right, on page 194, which is section 2.3. I want to go over a couple of these here. Number 87. All right, problem number 87, ladies and gentlemen. What would be the domain for this function? Notice this function, which is the plotting of these finite blue points here. The graph would pass the vertical line test because nowhere could you put a vertical line anywhere in a plane and strike more than one of these points at a time. So it is a function. What would be the domain? The domain consists of the x coordinates. And so what would be all of the x coordinates here? You'd have -3, you'd have -2 in the domain, -1, and you would have 2 in the domain and also +3. The range would be the set of all y coordinates. Well, the range would be consisting of -4, -3, +3, +4, and +5. That would be the range. All right, number 89. What would be the domain of this function? The domain would be the set consisting of all x coordinates of all points on the graph. Notice this arrow indicates that this graph goes on upwards forever. Okay. So what would be the smallest x coordinate of any point found in my domain? Notice this open circle here indicates that the point -3, 3 does not actually sit on the graph of this function. So -3, 3 is not a point actually on the graph. So would I include -3 in the domain? Yes or no?
No.
No, we do not include -3 in the domain. So the domain would be in interval notation, open parenthesis, -3, comma, up to what? What's the largest x coordinate of any point found on this graph? The largest x coordinate?
Infinity.
Positive infinity. So the domain would be not including -3 up to positive infinity. That would be the domain of that function there. So again, how do we represent that using interval notation? We say the domain would be not including -3 up to positive infinity. That would be the domain. What would be the range? Well, the range is a set consisting of all y coordinates of all points that sit on the graph. What's the smallest y coordinate of any point on the graph? Well, that's going to come from the lowest point on the graph. And the lowest points on the graph are points that have a y coordinate of +1. Do you agree? So +1 is the smallest value found in the range of this function. What's the largest y coordinate of any point on this graph? Well, this part of the graph goes up forever. So what's the range? It'll be including 1 up to what? Positive infinity? Do you agree? So the range of this function's graph is going to include 1 up to positive infinity. That'd be the range. Is this making sense how from a graph we are determining the domain and range of a function? Okay, does that make any sense to you?
Yes.
All right. Okay. All right. So, ladies and gentlemen, I have some problems for you to try out here. Now, one last thing is if we were given an equation for a function, the domain of the function is going to be the set of real numbers for which the function is defined. So I have a question for you here. If my function p of x is defined to be this function here, x plus 6 over x squared minus 2, when would this function ever get into trouble? When would this quantity ever be undefined? When you have a fraction, when does a fraction become undefined? When the denominator becomes what? 0. Isn't that true? When you have a fraction, if the denominator ever becomes 0, you have an undefined quantity. You can never divide by 0 in mathematics. So the domain for this function p of x would have to include all real numbers that do not cause our denominator to become 0. Because if our denominator becomes 0, this function is undefined. So to hammer out the domain for this function p of x here, we would have to look at the denominator. Specifically, we would have to look and see for what real numbers the denominator would become 0. So we're going to have to set this denominator equal to 0 and now solve this quadratic equation. Unfortunately, we cannot factor the left side, so I'm going to add 2 to both sides and then use the square root method to solve this quadratic equation. So I'm going to take the square root of the left side, take the positive negative square root of the right side. Hence, we see that if x is equal to positive or negative square root of 2, this function gets into trouble. Because if you try to put positive or negative square root of 2 into this function, the denominator would become 0, which means this function would be undefined. And so therefore, ladies and gentlemen, the domain of this function p of x must be any real number except positive or negative square root of 2. It cannot be positive or negative square root of 2. So how do we use interval notation to represent all real numbers except positive or negative square root of 2? Well, to do that, we would say the domain of function p would be from negative infinity up to negative square root of 2, but not including the negative square root of 2, in union with not including negative square root of 2, up to positive square root of 2, but not including positive square root of 2, in union with not including positive square root of 2 to positive infinity. That would be the formal interval notational way of saying the domain for this function p of x here would be all real numbers except positive or negative square root of 2. That's what this is saying. It's saying all real numbers except positive or negative square root of 2. Okay. All right, so for your last classwork here, what I want you to do is I would like you to do problems 1 and 2 here. I give you the graph of a function here, and I want you to, using interval notation, specify the domain and range. And then I give you a function defined to be g of x is x squared plus 3, and I want you to evaluate your function, or I want you to evaluate this expression using your function g of x. That means you got to put x plus h into this function first, and then subtract off g of x, and then divide that by h, and see if you can maybe simplify that there. All right, so 2 problems. Specify the domain and range of this function, and see if you can evaluate this expression by using this function g of x. Okay. All right, we'll call that the last classwork today. All right, for the domain of this function here, the domain, the smallest x value found in the domain of this function is going to be the point that's furthest to the left on this graph. Well, this graph goes down forever. And so the smallest x value found on this graph is actually going to go out here to what? Negative infinity. So the domain would be from negative infinity up to 1. But is 1 to be included in the domain? This point does not sit on the graph, but we do have this point up here that has 1 for its x coordinate, so 1 would be found in the domain. And we would go all the way up to 5 as being the maximum value found in your domain. So it looks like the domain would be from negative infinity up to 5, including 5. That would be the domain. The range is the set of all y coordinates of all points that are on the graph. And since this graph goes down forever, the smallest y coordinate found in the range would be negative infinity. So, and negative infinity is not a number, but so negative infinity up to 2. But would 2 be in the range? Notice this point's not on the graph. But just because this point don't have a y coordinate of 2, if you project it further to the right, you do strike a point on the graph over here that does have the y coordinate as being 2. So 2 is in the range. And so 2 is included. And therefore, we go up to a maximum y coordinate value of 4. That would be the range. Okay? From negative infinity to 4. All righty. All right, and this is being recorded, so if you didn't get this later on, you can watch this here. The last problem here, using this function g of x equals x squared plus 3, I want you to evaluate this. This is called a difference quotient. This becomes extremely important in your first semester of calculus, this construct called a difference quotient here. And to evaluate that, using function g of x, which is x squared plus 3, first we want to find g of x plus h, which means we put x plus h in for x. And so g of x plus h minus g of x divided by h is going to be x plus h squared plus 3 minus g of x is x squared plus 3 all over h. X plus h squared is x plus h times x plus h. And what does it mean to take x plus h times x plus h? Well, it means to FOIL this out. X times x is x squared. X times h is xh. H times x is xh. H times h is h squared. Combining like terms, xh plus xh nets us 2xh. And we get it down to this, but the x terms drop. X squared minus x squared drops out, and the 3's drop out. So your simplification of this difference quotient using function g of x, when all said and done, is going to be 2xh plus h squared all over h. And you can even simplify this even further if you want. If you factored out h out of each term in the numerator, then these h's would drop out here, and you would see in your first semester of calculus the importance of that occurring. And so you're left with ultimately of 2x plus h as the final simplified result of this difference quotient, which is g of x plus h minus g of x over h, using this function g of x, which is x squared plus 3. It all simplifies down to that. Okay. All right, so that's it for today, ladies and gentlemen. I hope you got something out of this, but I'll stay on the line for a couple minutes if you have any questions. But this whole session has been recorded, so you'll be able to, mull over this at your leisure later on. All right. So if there's no questions, you have a great day and great weekend. Yes, have a good weekend, and hopefully you can get that exam done. If you haven't done it, try to get it done by midnight tonight for chapter R and 1. Okay. All righty. There you go.
I have a question.
Yes.
So when you did the factoring in for when you put the overall given in, what did you exactly do?
We got to evaluate function g when we put x plus h into function g. So this x plus h has to go in for the input variable in the definition of function g of x. So x plus h has to take the place of this x here. You see that there? So
Yes.
x plus h has to be squared plus 3. So this, all of this is g of x plus h. Do you agree?
Yeah.
This is just what? G of x, correct?
Yeah.
That's g of x. Do you see it now?
Yes.
Okay. And then it goes on down from there. And it's just nothing but algebraic simplification from that point onward. And you get that thing all the way down to this in the end. Take it all the way down. Yeah. All righty. Any other questions or comments or anything? All righty. You have a great weekend.